Thank you. So hello everybody. So today we continue to talk about the single phase AC circuit. So I still remember that during the tutorial sessions, we have learned about how to calculate the powers of the single phase AC circuit. So here, this slide showing you the definitions of the powers in the single phase AC circuit. It is different from the DC circuit. That in the AC circuit, we have three different powers. The first one, as we learned in the tutorial session, that it is the average powers. So the average powers is defined as the products of the voltage, current, and another one is the power factor. As a matter of fact, that in practice, that when we have an impedance, if we have impedance Z, suppose the impedance has the impedance angle theta. Okay, then there is current go through the impedance. You had voltage cross the impedance. Okay, you have a current and a voltage. So as you know that the voltage, suppose the voltage is root mean square values V with the angle alpha. Then the current, according to Ohm's law, will be with root mean square values I with phase angle beta. Okay, beta. Here, according to the Ohm's law, that the current equal to the voltage over the impedance. Okay, over the impedance. So as a result, the beta equal to alpha minus theta. Okay, so suppose that in a circuit we have a component Z. This impedance has an impedance angle theta, and the current go through the impedance is I, and the voltage cross the impedance is V. Assuming that the V in Poynter form with a root mean square value V and with a phase angle alpha. Okay, then the current go through the impedance has a value I with a phase angle beta. The Ohm's law show that the current in compass number form, Poynter form, or vector form equal to the V voltage over the impedance. As a result, you found that the beta phase angle of current in fact is the voltage phase angle minus the impedance angle. In other words, the angles between the voltage and the current is the theta. So drawing in phasor diagrams, if this is the V vector and this is the current I. This will be the angle theta. Okay, so the V and now there is a angle difference theta. This difference theta comes from the impedance angles. Now you should understand the relationship between the current voltage phase angle difference and the impedance angles. Okay, as a result, the average powers, which is a scalar, is the voltage, which is a vector, dot products the currents. This is the vector dot products, okay, which is the value of the I and the I and the cosine okay. So the average powers, in fact, is the dot products of the voltage and the currents, which is the value of the voltage, current, and cosine theta, which is the angle between the voltage and the current in phasor diagrams. Similarly, that the reactive powers, which is the voltage cross products. Cross products. That means when the V and I cross to each other, the product is the maximum. So some students learn about the vectors products, some students not, right? So here we're just showing you the relationship. Do not ask why. This is the definition of the mathematical expressions of the dot products or cross products of the vectors. Sine theta. Okay. So furthermore, that okay, you can further write into the current square. That is the impedance you know, the Ohm's law, right? Which we have a cosine theta, right? Which can further be written into the current square the R, okay, the Z can be into okay. So that's the relationship. So here, as a result, similarly, so this can be written into the I square. So I'm just showing you, actually, you are able to, right, okay, derive these formulas too. Theta. And furthermore, it can be written into the voltage square okay, voltage square, and over the Z, okay, over the Z, okay. So voltage and so on. So the average powers can be brought into the V and I dot products, or VI cosine theta, or I square Z cosine theta, or I square R, or VR square over R. VR here means the voltage across the resistive parts, not the total voltage. Okay. Similarly, that the reactive powers is the cross products of voltage and currents, that which can be further write into the I square Z sine theta, and all the I square and the reactance X, or the voltage cross the reactance square over the reactance. Please prove it by yourself. Okay. Suppose that the Z is the series composition of the R, okay, with the Jx, and its polar form is Z angle theta. And here, a simple drawing here showing you that for an impedance Z with the impedance angle theta, the current go through it I with a phase angle beta, and the voltage cross it with a phase angle alpha. And the angle difference between the voltage and the current, that is the theta. That's the theta. Okay. So now the direct products of the voltage and the current is defined as the total powers, which actually in the DC circuit we using this one. Okay. Because in the DC the whole powers is the resistive powers, so there is no real powers, imaginary parts difference, so just the real powers. In AC circuit, we have the apparent powers, we have the reactive powers, we have the average powers. The average powers, as I mentioned in the tutorial sessions, also called effective powers, or sometimes called it real powers or effective powers. Some students may remember it, some students may forgot it. So real power, or effective power. So this is the powers, average powers is the powers consumed by the consumers. And the reactive powers actually is the power storage in an inductor or in a capacitors. Okay. So in most of the case, they do not using the words real powers, average powers, apparent powers. They just use the unit to distinguish between them. So if you read a books or read some of the questions, if the powers with a unit watt or kilowatt, this means the real powers or average powers. If the unit is the volt, volt ampere or kilovolt ampere, that means is the apparent powers, which just express the total powers go through and in a component. And if the unit using the volt ampere reactive or VAR or kVAR, this means the reactive powers. In most of the case for the capacitors, they're using the reactive power represent the power capacitors. Okay, for transformers, for example, so transformer just transfer the powers from one side to another side. So how much powers can transfer through the transformer? That is the total powers, apparent powers. So which using the unit of the VA or kVA. So pay attention to these points, because they do not use the word average powers, apparent power, reactive powers. They just using the unit to indicate the natures of the powers. Okay, this is the power issues. In next slide, we'll further demonstrate that what's the relationship between powers for different kind of the impedance. Looking at here, so we have a summary on in terms of the phasor diagrams to explain to you the difference between the voltage and the current, between the powers and so on. Now, for applying the voltage, for example, this is the voltage which has a phase angle values V and a phase angle alpha. So once again, someone may confuse this. Actually, can be simply write into the V with the angle alpha. Okay. And resulting currents. So I, resulting current I values root mean square values I with a phase angle alpha plus theta, plus theta. Then we can arrange them as showing below in figures. Of course, the theta may be positive and negative, right? But causing positive and negative is the same, right? Okay, so because the cosine plus minus theta, the cosine theta is the same here, actually, so this is minus plus, right? A positive and negative, Then we can sketch them as shown below in figures. So for power triangles, for inductive load, if it is inductive load, if it is inductive load, then the theta are in these directions, theta in these directions, In this direction, that the Langin power factors, it is Langin power factors. So then the total current, this is the total currents. This is the currents, total currents. This is the cosine currents parts. This is the sine currents parts. Components, that's the meaning of it. So that means this is the voltage, right? Direction. This is the voltage directions. This voltage directions. This is the currents in the directions of the voltage. This is the current perpendicular to the voltage. And then, so you have the power issues. So the total powers is, the total powers is the voltage current, that's this part. And the average powers is the voltage times the current at the cosine component and the cosine component. While the reactive powers is the VI product sine the component. Sine. So the average powers is in the currents in the directions, product current in directions of the voltage in the same directions. And the reactive powers that the current perpendicular to the voltage. This is the inductive load. Inductive load. So the current lags the voltage. So clockwise direction means lagging, means in the future. Not late. That means the current late. Than the voltage in terms of phase. Similarly, that for the capacitive load, if we have capacitors, capacitive load, then the current is the voltage. The current reaches the peak values before the voltage reaches the peak value. That's the meaning. Then, in general, the voltage across a capacitor and the current through a capacitor, the current leading the voltage across the capacitor and the current right through the capacitive load, then the current leading the voltage by angle theta. That's mu. Okay. Similarly, we have the currents that's in the voltage direction components that perpendicular to the voltage components. Then you have the power triangles, then the total powers or apparent powers. Okay, apparent powers. You have the average powers, which is the power consumptions by the resistive part of the capacitive load. So, this is the reactive powers. Similarly, that this is the impedance Z. Okay. For inductive load, the theta, is between 0 the angle, right? For capacitive load, the angle, right, is minus 90, the angle, Remember, in practice, if it is an inductive load, then the impedance angle theta is between 0 and 90 degrees. If it is a capacitive load, then the impedance angle is between minus 90 and 0 degrees. As a result, for the inductive load, that the current lags the voltage by an angle theta. For a capacitive load, that the currents leading the voltage by an angle theta. So in practice, when you write into a capacitor into a impedance with polar forms, then the angle, phase angle, the impedance angle should be negative values. If you write an inductive load into a polar form, the impedance angle should be a positive values. Remember these points. The impedance angle always is between minus 90 and plus 90 degrees, while the phase angles may be quite different from each other. This is the power triangle issues. So now you should understand for the inductive load, capacitive load, that their powers, their voltage, their current, the relationships in terms of the phasor diagrams. This here slide is the phasor diagrams showing you the relationship between the voltage, current, powers for a given load. The load may be an inductive one, may be a capacitive one, may be a pure resistance, may be a pure inductor, or may be a pure capacitors. Here we have a summary on, so the complex number forms, right, calculation of the powers. So because it is a vectors or complex number of forms or Poynter forms of voltage, current, and impedance. So we can do the calculations separately or doing the calculation directly using the complex number of form, right? Okay. Okay. The above triangle also can be expressed by using the complex numbers forms as the following. Suppose that we have voltage which has values V, mean square values, with impedance phase angle alpha, which in the Poynter forms or exponential forms. This is Poynter or exponential forms. That we have a current, then the current can be written into the Poynter form or exponential form. Okay, that with impedance phase angle alpha plus the thetas. And then, okay, the conjugate. This is the conjugate. You still remember conjugate of the currents. Okay, so the original vector or complex number form or the Poynter forms. This is the conjugate of the Poynter form or the complex number forms, which you just simply change the phase angles into negative plus. You can add a minus sign to the phase angles and a minus sign to the phase angles. Okay, then the total powers can be simply written into the voltage times the conjugate of the currents. Conjugate of currents. That is the voltage with a phase angle alpha and current with a phase angle minus alpha plus theta. Okay, which is the voltage current minus theta. Okay, which can be further written into VI cosine theta minus VI sine theta. Because here in the theta alpha theta, we use the plus sign here. So as a result, this is minus. If in an inductive one, this is a minus. Okay, depends on the angle theta's values. Okay, in cyclic right forms. Okay, sorry. Then it will P minus J theta. Q. Here, the P is average powers, the Q is the reactive powers, Okay, so that's the relationships. But of someone, of course, if you change this, negative. Then they will be plus. Okay, so to avoid confusions, so if you have V alpha and I has an I alpha minus theta. Okay, and alpha minus theta. And then you will have you have the VI E positive theta, or VI cosine theta plus the J VI sine theta, or P plus the Q. Remember, it doesn't matter. Okay, you can go P and Q. P is the average powers, Q is the reactive powers, and so on. Okay. because here we use the symbols, not use the actual angles, so it doesn't matter plus or minus. It depends on the angles values, which is maybe a negative, maybe a positive, doesn't matter. Okay. And then the average powers. So you can further write into the average powers is the product of void currents cross that impedance. Now we are talking about one impedance. Okay. So that's the cosine theta, which is the impedance angles. Okay. And the I square of the resistance, okay, or the VR square over the R. Okay. So here the impedance, once again, we have impedance value with the impedance angle theta. Okay. So suppose we have the impedance is, okay, with the impedance angle theta and with the resistance R with the reactance X. Okay. Then the total voltage cross the Z is V. The current through the Z is I. The impedance angle is theta. Then the powers consumed by this impedance is VI cosine theta. And furthermore, can write into the I square, the resistance R, or the voltage drop cross the resistance over the R. Once again, VR not equal to V in the series one, not equal to V. Okay. Or the real parts of the VI products. So that is the total powers S in comes number forms, the total powers, these total powers, which comes from the P and the Q. Okay. The values and power angles. Okay, you can go. So this is the real parts of the powers, which is the P. Okay. Real parts of the S. Okay. Similarly, this is imaginary parts, okay, of the total powers. That's the meaning of it. Okay, average powers. Okay, the relationship between the voltage currents and the powers, the currents and the resistance and the powers, the voltage drops cross the resistance and the resistance, and the total powers and voltage currents. So reactive powers, that is the VI sine theta, that is the I square, the reactance, or the square voltage cross reactance over the reactance, or the imaginary parts of the total powers. And the total powers of the values can be simplified, simplified as the products of the voltage current values only, or the I current square and the impedance, or the total voltage cross the impedance. This is the voltage, the impedance square over the impedance. Absolute values of the VI, absolute values. Which is the P square over the Q square. Triangle relationship. Okay, the total powers actually is average, average power square plus the reactive power square root. And here someone said, why you write a VZ? So we have a VZ, that means the voltage cross the Z, given Z. Okay, that voltage VR means the voltage cross, okay, the given impedance, the voltage cross X. What does it mean? That so the VZ actually here is total voltage, right? So suppose we have an impedance, that impedance can be brought into in series this is R, this is X. You have voltage here. You have voltage here. Okay. Okay. That's the relationships. Okay, the different triangles. This means that okay, triangles. Okay. That means okay, this is okay. So suppose you have an impedance. So the impedance can be written into series equivalent R in series with X. Then you have voltage cross R. You have voltage cross the X. You also have the total voltage cross the impedance. Then the impedance angle, okay, impedance voltage related to the voltage VR and Vx, okay, which VR is the real path, okay. Suppose that the Vx path, which in a triangle, suppose the VR is horizontal and the Vx is okay, vertical, then the Vz. Or this depends on okay, how you draw it. Or in some, right, you may draw this is the Vz. This will be VR, this will be Vx. This will be theta. Okay. So their relationship, suppose you have VR, okay, you have V in this direction, and Vz in this direction, the VR in this direction, and then Vx will be in this direction, and they have an impedance angle theta, okay, and this will be 90 degrees. This will be 90 degrees. So this is the phasor diagrams. So when you draw in phasor diagram, you can define one component, the phase angle, as 0. Then for the other parameters, you can refer to this reference to draw the angles. Okay. So when you try to draw a phasor diagrams, you can define a reference angle as the 0. Then the other angles refer to it. Okay. In most cases, we choose one voltage, particularly the total voltage or the source voltage, as the reference as the reference. Then the other components can refer to this reference to draw their angles. Okay, so and furthermore, that the power factors which define as the cosine theta, which is the right impedance angle theta, cosine theta, which furthermore actually is the ratio between the R and Z, or the P over S. P average powers is the apparent powers. Here we just consider about the values of it. So actually, this slide summarizes the difference in terms of the powers between the AC circuit and the DC circuit. Pay attention to these points. In addition to the complex number forms, the impedance, the voltage, and current. The power issues is another very important issue in the single-phase AC circuit that frequently, right, the students ask questions about it. Okay, remember the calculations of it. This is the power issues. Okay, students may find that there are many formulas here, but this formula actually is logically is not a formula. It's just derived from the original Ohm's law. Okay, this is just a change of the Ohm's law. If you know the Ohm's law, and if you know how to express and calculate the complex number forms, then you can automatically got all of these formulas showing here. Okay, so similarly, that to the DC circuit, in the AC circuit we may have networks, AC circuit networks. So the networks may involve several nodes, and involves several impedance, involves several the source voltage. But here we just based on one simple source to showing you how to find out the Thevenin equivalent circuit of a complex number, complicated networks. Because in a circuit maybe that some parts of the circuit be fixed, no change. Some parts of the circuit always changing. So to simplify the circuit, we had better use the Thevenin theory to simplify the equivalent circuit so that the analysis of the circuit be simplified. Suppose here, so the principles is quite similar to that of the DC, but the calculation, we follow the complex number forms rules. Suppose now we have a source that have root mean square values Vi, which has an internal impedance Z1, and in parallel with the impedance Z3, and then in series with the impedance Zn2. Okay, and then so its output terminal is A and B. Okay, we think that the A and B, this terminal, is the two-terminal source. Then the part in the left of the AB can be simplified in one simple source, as shown by the A prime, B prime here. Okay, so this circuit can be equivalent into a simple circuit that is internal electromotive force E in series with an internal impedance Z. Then the two terminals are equivalent. Okay, we can see. Then thicken that when this source, when this circuit AB is open, A prime and B prime is open. So the VAB, and here the VA prime, B prime will be E, right? Okay, when they are open, there will be E, right? Will be E. Okay, will be E. Therefore, for equivalent circuit, so because for the right side, these figures that you can see that the internal electromotive force E equal to the terminal voltage V A prime B prime when it is open, because when it is open, the current will be 0 between AI and A prime and B prime. Then there is no voltage drops across the Z. Therefore, the terminal voltage equal to the internal voltage because the current will be 0. Okay. Okay, so this is the presupposed open circuit, right? When it is open, because the current be 0, then the voltage drops across the Z be 0, and as a result, the terminal voltage V A prime B prime equal to the E. That's it, equal to the E. Now, suppose this circuit be equivalent to this circuit, then the terminal voltage must be the same. That's the source, because right, must be the same. So we are talking about equivalent circuit. So the V prime, A prime, B prime should be equal to the AB when the AB terminal is opened. Okay, that's why we say the Thevenin voltage E is the open circuit voltage at terminals A and B. Okay, that's it. Okay, that's it. Okay. So now, similarly, that the impedance, the Thevenin impedance Z is the impedance C and the AB with all voltage sources replaced by the short circuit and all current sources replaced by the open circuits. Okay, look at here. So the Z actually is the total impedance looking into the systems from Z A prime B prime with the source be short circuit, right? Source be short circuit. Okay, short be short circuit. So similarly, that the impedance is equivalent to the impedance looking into the network from A and B with the source, voltage source be short circuit. Okay, when voltage source be short circuit, that means the total voltage here. So that means as a result, look, that the current first we can find out, okay, the current in this row, in this, right? When this open, the current here okay, when the AB open, that the current go through the Z2 is 0, and the current in the loops I is V1 over Z1 and Z2, Z1 and Z2. Therefore, the voltage VAB that is the currents that V1 this is the currents, right? This current times Z3, okay, right, is the V3, right? Okay, so the internal voltage E equal to the V3, that the voltage cross the Z3, plus the voltage cross the Z2. But Z2 equal to 0, right? Okay, Z2 equal to 0. So the equivalent, right, voltage, internal equivalent voltage, okay, equivalent voltage, that is the, okay, that is, okay, the V3 plus V2, and the V2 be 0. Okay, V2 be 0. Okay, voltage. Okay, so this is the voltage. So you can estimate voltage by this one. But how about the impedance? Impedance. The equivalent impedance, that is the, okay, look at here. When using the, okay, short circuit represent the V1, then you have the Z1 and Z3 in parallel, and they're in series. Parallel. Remember, you have to use in the constant number form to the calculation. They have the, okay, okay. Okay, so you look that we use the same forms that can used for the DC circuit for your easy understanding. But this just show in the principles that the Thevenin theories is the same as that in the DC circuit. But we have to take care that the impedance here, voltage here, and the current here are all in constant number forms. Numbers. Okay, so this is the internal equivalent impedance and internal electromotive force relationship between the Z1, Z3, Z2, and V1. Okay. So suppose given that the Z1, Z2, and Z3 and V1 given, with the V1 as the reference. Okay. Okay, you can define that the voltage V1, which has a phase angle 0 degree, 220 0 degree. Then you can find out the Thevenin series voltage, and therefore, furthermore, you can find out the current in the internal loops. They have the values and phase angles. And similarly, that impedance will have the impedance angles. Impedance angles. You can write into the impedance into Compton number forms or Poynter forms. And for the voltage, you can write into the Compton number forms or Poynter forms. Poynter forms with angles. You will find out that. Please test yourselves by doing these examples. You just simply to bring in that the impedance values Z1, Z2, Z3, and V1. So you can find out the equivalent impedance Z and the equivalent internal electromotive force E values. As a practice, checking your understanding of the Compton number forms calculations. Once again, we're doing the summations or subtractions. You can use in the Compton number forms. When doing multiplications and divisions, suggest you using the Poynter forms. Therefore, for each of the impedance, each of the voltage, you can write them into both the Poynter form and Compton number forms. Of I strongly suggest to write each component into both Poynter and Compton number forms for easier calculation and conversion between each other. So do not be lazy doing that. So to avoid mistakes during the calculations, once you got the result for a component, write it into both Poynter form and Compton number forms. So that will be perfect. This is the Thevenin theories that is so you can use in the same principles we use it for DC circuit, but pay attention to the Compton number form calculation. So for better understanding of the Compton number of calculation, you have had some practice such like this to do the calculation to check your calculation capability to get yourselves familiar with the calculation of the Compton numbers. Power factor corrections. Now we touched about the apparent powers, touched about the real powers, touched about the reactive powers. That in most of the industry and residential buildings, that we have inductive powers. That means that, for example, that the rotation, that the motors, that the transformers, that the refrigerators, that whatever machines, rotary machines, such as the washing machines, they are all inductive one. As a result, the current lags the voltage. So you still remember that in power triangles, then a hypotenuse, hypotenuse, hypotenuse S is a measure of the loading on the distribution systems. That means the S represent the total powers go through on the transmission or distribution lines, okay, which corresponded to the total current I. And the P is the okay, and the side P, that is average, is the measure of useful power delivered. It is therefore that designed to have the powers on the distribution systems close to the powers to be used. So how to making the P close to the S? Okay, so for inductor load, it is often possible to improve the power factor by placing a capacitor in parallel with the load. Since the power factor is increased, the current I and the apparent power S decrease, making the distribution systems more efficient. Okay. What does it mean? That in practice, the true powers, okay, is the P is the power to be consumed. Suppose the powers to be consumed is the same. Power to consume is the same. If we have a bigger cosine theta, then the current required on the distribution system will be small. P is constant. V is constant. If the cosine theta is bigger, the I will be smaller. So the I be smaller means that the current on the distribution system be smaller. And on the distribution system has a power loss of I fair and resistance okay. So the distribution systems maybe are 10 kilometers long, maybe 1 kilometer long. They have the transmission lines. The transmission line has resistance. So therefore, if we have currents, then the transmission line has power losses. So the power losses is the current square times the resistance, wire resistance. So the distribution system has power losses. If you can reduce the current required by improve the power factor cosine theta, then you can making the power losses on the distribution system be smaller. You know the inductance has a power factor. Inductance has the angles being negative. Be positive, and the capacitors has a impedance angle negative. So two together making the impedance angle be smaller. Okay. Has a negative okay. So inductive load has a positive impedance angle, and the capacitive load has a negative impedance angle. So inductive load in parallel with the capacitive load, making that the total impedance angle on the distribution I will be smaller. That's the principles of the power factor corrections. Okay. 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 So combinations of capacitors in parallel with the inductive load and makes the total power factor of the system bigger. Okay, that's the corrections, the power factors. So you also can prove this one by doing some of specific calculations. Okay. So we have already started by example 1 in tutorial sessions. Here we do not talk it again. We just go through it. Example 1 in tutorial sessions in the Tuesday. Example 2 also we talked about it. Now we come into the transient analysis in the AC circuit. And then normally that we expect that the circuit to be a normal circuit, that there is no short circuit, there is no open circuit. Okay. But in practice, maybe because some accident, because some interference, external interference, that the system, the short circuit or the fault occurred in the systems. Then there will be some transient phenomena. The transient current usually be very big, which damage the systems. So to maintain the systems be safe, we have to design systems by taking by considerations of the transient currents issues. Okay, we should install some protective devices so that system can be protected against the short circuit, against the transient big currents. Now, so in practice, we have several kind of the transient phenomena. So suppose that we have the A, B, C drawings here. So the short circuit points occurred at different places. Okay, for the consider simple issues that in figure A, that inductive load. Okay, inductive load, that means we have the resistance plus the reactance. It's supplied for the single phase source. This single phase source with a voltage V and normally with a current I to 8. And the second case that we have a generator which has an internal resistance. Generator itself has internal resistance R plus JX. And the terminal usually has been supplied to a load, but by accident there is short circuit occurred here. Okay, we use the switch here represent short circuit occurrence. currents. Okay. Anyway, so in our case, that the short circuit may occur at a different place as we show in the C. Okay, shown in C. In either the case A, B, and C, their transient phenomena similar. The response of the circuit similar. Okay, we using the switch here represent the short circuit case. Now, so using the ohms now, suppose that the voltage, right, we supplied, voltage we supplied is a sine waveform with a right phase angle alpha, okay, with an angular frequency omega. Okay, so the instantaneous voltage V, because now we are talking about the transient analysis, we have taken account the transient, right, instantaneous values of voltage. So suppose we have the instantaneous voltage V, which has a max value V with a sine waveforms and phase angle alpha. It is supplied to the impedance. The impedance as shown in the previous slide. So we have a voltage V supplied to impedance R plus JX, and when the switch on, and the moment the switch on, okay, and the moment switch on, that the voltage supplied to the voltage, okay, currents go through the resistance R, and the current go through the inductance L, which omega L will be the X, Then this is the Faraday's law, right? This Faraday's law, okay, where alpha is the voltage, right, phase angles when a switch is closed. At the moment, here we use a switch to represent the short circuit case. The system has a voltage running there, and at one time you switch on. So as a result, at that moment, the switch phase angles, okay, the angles is not at exactly omega t equal to 2 pi, or omega t equal to 4 pi, 3 pi, and 4 pi, just okay, at different places. Okay. Okay. Assuming that the circuit is a linear circuit, then the solution is linear means okay. Linear means that is a constant, right? Impedance. Okay, it means a constant impedance with times. Then the solution is right. Okay, so this is very similar to that of the DC circuit, but here because the voltage is sine waveforms, therefore the solution also is sine waveforms. Okay, the values sine wave, but E minus T over T in the same. Okay. You can Google right on the network website, Google, find out solutions directly. Here I do not explain to you. This is general solutions of it. Okay. Here the phi is the phase angles comes from the impedance angles. So where the reactance X equal to the omega L, which we learned previously, and the impedance, which is the R square plus the reactance square, and tangenta, right? Theta, which is the impedance angle, actually, is X over R, or the T, and the T is the time constant. Okay, so this t here represents the time constant, which represents how long that the systems take to achieve the balance or achieve the balance case. Okay, balance case. Stabilized. Okay, stabilized. Okay, so this is time constant. Okay, time constant, which is the inductance over the L. Now, looking at this inductance constant, if the inductance L is 0, then this time retarding times will be 0. That means the current achieve its stabilized values, okay, at the same moment that you switch on. If the inductance is big, then the T will be big. Then the current, okay, will take longer times to achieve its maximum values. Okay, maximum values. Here, the Vm over the Z is the stabilized values, the maximum values, and sine alpha minus theta, and E minus T over D. This represents, okay, that the changings, okay, of the current from the time 0, switch on time 0 to a given times, okay. So showing here that, okay, the first term actually is E-type exponential form. The sine alpha minus theta, which event is a constant, right? Once the alpha is given, phi is given, sine alpha minus phi will be given, right? Vm over Z is a constant. Sine omega t plus alpha minus theta, which are sine waveforms, right? Sine waves, okay, which has a phase angle difference from the voltage. The phase angle difference is the phi, which is the impedance angles. Okay, impedance angles. Okay. So remember that voltage current always has impedance angle difference. Okay. Then we can see that the first term, okay, the second term, this is I DC. This is I AC. So the first term is IDC currents because that it is right polarities keeps the no change, although the values change. Okay, which is exponential, okay, exponential forms. And the second terms is the AC current, which is polarities changing with times, which is the sine waveforms. So here in the drawings here, that the IDC represented by a solid line as here IDC, and the IC represented by the dashed line sine waveforms, and the total current I, which is the curves, sine curves, superposed on a DC component. So the sine waveforms superposed on a DC component, which is the I, correct? So you look at the starting points. If so no, if it is stabilized, look at here, this bit stabilized the currents. This is the transient moment. Okay, so you have the transient moment current. You have the stabilized current. The transient moment current is much larger than the stabilized moment current. Depends on the sign alpha minus t and minus phi. Suppose the sign alpha minus phi is 1. Then this term, right? This term, okay, has additional currents to the sign waveforms. So transient moment current much larger than the stabilized current. Okay, much larger than currents. Okay. So that's the difference between the stabilized current and the transient moment current. So in the AC circuit, whatever AC circuit, you at any moment you have the switch on and the switch off process, right? Even in the normal case, switch on because it's a transient starting current much larger than the smallized, okay, than the stabilized currents. Even in a normal circuit, the current and the moment might be much bigger okay. Okay, so that even in a normal circuit, the current at the moment of a switch on might be much bigger than the stabilized currents. So that's the case of it, right? So which will be harmful to the circuit healthy. So therefore, in practice, for is particularly for having currents, when there is current very bigger on the distribution arm, you should be careful when you switch on. Okay. So therefore, when there is a very big current in a distribution system, the switch on cyclically is important. So therefore, when there is a very big current in a distribution system, the switch on cyclically is very important. Is very important because that we do not want to make the switch on current much larger than the stabilized currents. So otherwise, that we're talking overheating, we destroy some of the switch systems in the distribution system. Okay. Now let's have a discussion on how to make the transient starting current be smaller. Look at here. So if we can make that the sine alpha minus switch, okay, switch on, okay, alpha minus the phi be 0, then this switch on current will be minimized. Okay, will be minimized. Okay, sine alpha minus theta. Okay, remember these terms. Now Okay, so from the above solutions, we can conclude that if the alpha, which is the switch on angles, and phi, which is the impedance angles, if the alpha minus phi equal to 0 or pi, then the DC component will be 0. If the switch on angle alpha and minus the impedance angle phi equal to 90 degrees or 270 degrees, then the DC component will be the maximum. Okay. And for cosine theta equal to 0 or the resistance equal to 0, then the phi will be 90 degrees. If the switch angle will be 90 degrees, then DC will be 0. If the switch angle will be 0, then the DC component will be maximum. For different order, right? So for cosine theta equal to 1, there the inductance, okay, will be 0. That impedance angle will be 0. Then the IDC will be 0. Okay. So if the R be 0, I be 0. So in general, that the R and X will determine the maximum likely DC offset, and therefore the peak current that can occur, as well as the rate of the decay of the transient. Okay. Rate of decay of transient depends on the retarding time constant D. The general principle shown here is applicable to similar three-phase system for lattice, modular startings, and so on, which we will learn in the chapter 4. Okay, next week, we will learn about three-phase systems. So here we just have analysis on the transient, right, phenomena, switch-on phenomena, which, right, we should pay attention to it in the DC circuit, because the DC circuit has the bigger transient starting currents. Okay, of course, right, example 4, okay, you can try by yourselves that I can bring in that's the resistance, the inductance, okay, into the previous slide, the formulas. So giving that's the voltage here. So voltage here given, right here given. So just the 150 is the maximum values. The 500 is omega. Is the phase angle. Okay. So that this R, this is inductance. This is the 500 is the omega. 500 is omega. Okay. So the inductance L 0.2 henries. The reactance omega L can be simply estimated. So suppose that apply and time 0 equal to 0. Okay. Calculate the peak values of the transient currents. Okay. Okay, right. So when you switch at time t is 0, okay, you can estimate the peak values. Peak values using the previous formulas given here. Okay, you can estimate peak values. Example 5, which we okay. So you also can write using example 5 in the chapter, right? Use the example 1 and okay, example 2 that in the chapter, okay, in the chapter 2, there the inductance, okay, the inductance Okay. You also can do some calculations based on the example 1 and example 2 in the chapter 2. There you have the resistance R, you have the inductance L. Example 2, you have resistance R, you have inductance L. Then if you have 110 volts AC root mean square values, then you can calculate. Okay, so the voltage root mean square values, right? 10 volts is the root mean square values. This is the peak values with the sine waveforms, 50 hertz. Okay, so given that voltage is 10 volts, okay, root 2, that is peak values, because given 10 volts, that is sine 50 hertz, 100 pi t plus the phase angles. Okay, so this is the V. So with the V, right? With the L, with the R. Okay, so you can use in the R and L in the example 1 and example 2 in chapter 2 with the given voltage waveforms here. You can estimate that the peak values of the worst values, that means peak values of the transient currents. Okay. Example 4, example 5, actually giving you an exercise to familiar with yourselves with the transient calculations. Okay, we do not talk in detail about this one in the tutorial session because it just is a simple practice of the calculations using the concepts of the transient analysis. Okay, so you can try it by yourselves later on. Okay, so lastly, we have talked about the cables and conductors in the AC circuit. Different from the DC circuit. The AC circuit, the current has frequencies which change with times. Because that's the frequency issues, the current on the conductors not uniformly go through the cross-section of the conductors. The current tends to flow on the surface of the conductors. Tends to flow Okay, so generally the current tends to flow on the surface of a conductor depending on the current frequency and conductivities. Okay, conductivities. So when the frequency is 0, that's the DC, the current go through, okay, current so flow uniformly in the AC case, the higher of the frequency is, the thinner of the surface, right? The current flow. So in the AC circuit, that when the frequency is very high, that the surface part of the conductor is very thin, very thin. Okay, the thinner of the surface of the current flows. Okay, that's the skin effects. As a result, because the impedance resistance depends on the cross-section area, effective cross-section area, okay, as you know, okay. And for a given conductor, that's the resistance equal to the resistivity times the length for conductor over the effective cross-section area. So when the effective right cross-section area where the current flows will be smaller, then the resistance will be bigger. Okay. So therefore, in an AC circuit, because the effective cross-section area of conductor becomes smaller, therefore the resistance becomes bigger. For example, from the tables on the but here from data tables, that we were showing you right later on the tables. Then the DC resistance and the resistance at 50 Hertz values differ. They are different. The resistance for 60 Hertz are higher than the resistance for 50 Hertz. Okay, that's the meanings we said there. Okay. Okay. Similarly, this is skin effects. So in cables with armory skin effects and calculating right, the currents in the armory can cause additional problems due to the heating and circulating currents. Okay. So for large cables, the inductance becomes the larger component of the impedance. The inductance is the back leakage inductance. So okay, here in the cable's inductance, actually in chapter 2 already showing you that there are some flux outside the conductors. The cables may be one core cable, two core cables, or three core cables. Between the cores, there are some space, free space, or the space be inserted with the insulation materials. Depending on the materials, the leakage inductance will be different. Okay, so this leakage inductance varies with the spacing of the conductors. Okay, So the inductance, therefore, we have the inductance resistance, inductance. Okay, the resistance, reactance, okay, therefore you should remember that the resistance changes with frequency and also change with temperatures. So sometimes, okay, they change with frequency, some change with temperatures. So in given, okay, readings that the frequency unit is fixed. For example, in Hong Kong, 50 hertz we used here. The reactance, that which is the product of the omega L, omega is the frequency, right? Angular frequency, change with the frequency. Change with frequency. Okay, this is the important issues. For examples, if you have reactance, impedance, reactance, and 50 hertz, okay, and 50 hertz is 50, then if you come to the 60 hertz, it will be 60. Come to the 100 hertz, will be 100. Okay, so you look that when you have a reactance and 50 hertz is 50, then the reactance and right second harmonics of it, that is 100, right, and the third harmonic will be 150, and the fifth harmonic will be 250, and so on. So this is the properties of the resistance and the reactance in the AC circuit. Please remember these points, okay, which will be checked or examined, okay, in the assignment 2 and in the final examination papers, which will be examined, okay, asking you to do some calculations. Okay, you remember these points, otherwise you make mistakes of it. Okay, that is the cable's conductance. Since we have the resistance, reactance, and the impedance, therefore we have the resistive voltage drops, we have the reactive voltage drops, we have the total voltage drops, which will be reflected in the data tables too. Okay, in the DC case, that we just have the resistive voltage drops, but in the AC circuit, we have three kinds of the voltage drops, which corresponding to the resistance, reactance, and impedance respectively. We will talk in detail about the data tables in the tutorial sessions before we doing the calculations of some of the examples. Okay, here tutorial examples which we will talk in tutorials. Okay, for example 2, which we will talk in tutorials. Okay. Okay, so that's the end. That's the end on the lectures on the single phase AC systems. Please okay, taking certain times to have a revision on the principles of the single-phase AC systems. Particularly, to learn how to present, right, the voltage, current, and impedance in both polar and complex number forms. And also get yourself be familiar with the calculations of the complex number forms and the polar forms, which is the big difference between the DC and the AC. Okay, so if you still have some questions or confusions about the AC single-phase AC circuit, okay, you can write to me, okay, using the chat box now, or you can write to me using the emails later on. Okay, before you get questions, please, okay, once again take revisions on the radio's, okay, recordings, so that you make sure that your questions be due questions. Okay. Okay, that's the end of today's lecture. But okay, we still have a few minutes that you can ask me questions, okay, or write down your right suggestions on the single phase ACs.